Hello students, I'm very excited that we're doing section 5.5. This is the last section and we're going to finish it off with a one question that essentially summarizes or reviews the whole chapter 5. So this section is about determining if a relationship that's presented to you is either linear or nonlinear in a different way than what we've done so far. Up to now, how we determine if something linear was nonlinear is maybe we got a table of values, we would graph it, we would see if it has a line or a curve of best fit, and that's it. The problem with that is it's very time consuming, it's a lot of work. So this method is gonna give you the answer much faster, and you probably already noticed how it works, but you didn't have kind of the proper terminology. How it's going to work is that usually you are given a table of values, and essentially what you have to see is are the y values increasing by the same amount all the time. So in this first example, we have x 0, 2, 4, 6, and then the y values are going up by plus 8. So plus 8 every time, plus 8 every time. So the amount that it's increasing is called first difference. And that's what really this tool is called. It's called finite differences, but really we're focusing just on first differences. It's just describing the differences between the y values. If we look at the second example, if you don't have the same increase every time, that means it's going to be a nonlinear relationship, a curve or something else. So as you can see here, it's increasing first by 1, then by 3, then by 5. Now this also works with decreasing. It could be subtracting by the same amount or a different amount. So the key here is if your values, if these first differences are the same, that means that what you have here is a linear relationship. If they are different, like these ones, that means it's not linear. The most important, well, not the most important thing, another thing that you should pay attention to is your x values. You should see if they're increasing by the same amount, if they're changing by the same amount, or they could be decreasing, but you should see if they're changing by the same amount. So in this case, it's going up by 2, in this case, it's going up by 1. As long as they're the same, and then you can see that the first differences are the same, then you can say that this is a linear relationship. All right. The problem with this method is that you can't really do any uh, easy estimating, interpolating, extrapolating. So that's why it is useful to have some, graphs and so on. So that's it. That's it, the lessons. So I will show you how officially we do the first differences. There is an example here, but actually I'll use the example. So it says here we have two table of values. We'll determine if the relationship is linear or nonlinear. And this is what I want to focus on. As you can see here, we have the x's, they're increasing by 1. Y's are increasing by some amount. So how we find the difference is we take this second y value and we subtract from it this first y value. So that's why it's 3 minus 1 and it's 2. So that is the value for the first difference. And then we slide down. So we kind of did these two. And then for the next step, we slide down and we focus on these two. And then we subtract 8 minus 3, and in this case it's equal to 5. And then we keep going. We slide down again and focus on just these two. And 26 minus 8 is 18, and so on and so on. You might have noticed that these numbers are not the same, so this is definitely not linear. Um, the most important thing is when you're actually performing the first differences, you have to take the bottom number minus the first number. So second minus first. So in this case, we had 3 minus 1, not 1 minus 3. 8 minus 3, not 3 minus 8, and so on and so on. You could probably determine if something is linear or nonlinear, but you're going to get the wrong first difference. And these values for first difference are actually very important, as you're going to see in the next few chapters. So this is nonlinear. I'm sure it's written somewhere here. Yeah, so it's going to be some kind of a curve of best fit. There we go. If we do the second one, which is B, again, you're taking two at a time, and you're taking the bottom one minus the top one. So 55 minus 58, which is negative 3. 51 minus 55, negative 4. 48 minus 51, negative 3. So as you can see here, these are not all the same. So this is also not linear. And I'm reading it. This table of values is better represented with a line of best fit. Um, that would be wrong because first differences are the same, then the relationship is linear, but these first differences are not the same, so this relationship is not linear because it goes negative 3, negative 4, negative 3, negative 3, negative 4. So I think they are wrong here, unless I read something incorrectly. So you have to have all of the numbers the same, all of the first differences the same, otherwise it's not changing by the same amount. So 58 is negative 3. Yeah, this is definitely not linear. This cannot have a line of best fit. So yeah, we found a mistake in the book. All right, so let's apply this to our examples. Here we go. Um, each table of values represents a relationship. Use first differences to decide if the relation is line of best fit or curve of best fit. All right, so remember, we take two at a time. I check the x values. They're increasing by 1. That's good. In this case, we take the first two, so I have 5 and 11. So I'm going to kind of write it like this usually. 11 minus 5, which is 6. And then I slide down. 17 minus 11, which is also 6. Yay. And then slide down. 23 minus 17, 6. And 29 minus 23, also 6. So, based on this, our first differences, that's what these numbers represent, are the same or constant. And because of that, this should have a line of best fit. So I'll write it first, actually, that this is linear. And it does say use line of best fit, I'll say. Use line of best fit. That's kind of redundant, but you know, it's linear because we are using line of best fit. So yeah. All right, next one, same thing. I'm gonna check my x values. They're also increasing by the same amount, so it's good. And then I'm gonna take two numbers at a time. So I have 80 and 40. A lot of time people get confused and they take the bigger number minus the smaller number, but that is not the case. You always take whatever the second number is, in this case 40, minus the first number, which is 80. So in this case, the answer is minus 40. And then I slide down and then take 20 minus 40. In this case, it's minus 20. Slide down again. 10 minus 20 is negative 10. And hopefully by now you can see this is not going to be linear because these first differences are not the same. They're not constant. So I'm going to put non-linear. There we go. And we're going to use a curve of best fit and so on and so on. Here we go. Moving on to the next one, it says Sandra has been measuring the height of a flower for 5 weeks. Her data is shown. Is the growth of the flower linear or nonlinear? Use first differences. So we could graph this, but it's going to take too long. So we're just going to use first differences. We're measuring for every week, or Sandra's measuring for every week. So we're going to take two numbers at a time. You'll 10.1 minus 8.0. I'm just going to write all of them out. Then I slide down. 11.9 minus 10.1. 14 minus 11.9. 15.8 minus 14.0. There we go. And then you get your trusty calculator because there's a few decimals here. It's not really too difficult, but I'm going to use it anyways. 10.1 minus 8, 2.1. There we go. I find that when I do these videos late at night, my brain is not functioning as well. And 14.0 minus 11.9, 2.1. And I'm guessing the next one's going to be 1.8. 8 minus 14. Yes, 1.8. There we go. So what we see here is that the first differences are not um, the same, and therefore we're going to say that it's nonlinear. There we go. That's it. Now, if we were on a graph and maybe we would put that this is linear just because we'd have some points above, some points below, but based on first differences, we're going to say, no, this is nonlinear, and the first differences are not constant, and that's it. Moving on. All right, this question. Okay, so this is, I think this is the last question of this section. Yes, so this question, I'm going to do it because it reviews everything. So everything from the start. So the table of value shows the value of a car over several years. We have that, age of the car from 0 to 4 years. We have the value from 20,000 to 8,000. Does there appear to be a relationship between the car value and its age? So we're looking at the two variables, age of the car and value of the car. And hopefully you can see that as the car gets older, so I'll write it, as the car gets older, the value of the car goes down. There we go. That is a relationship. Or we could say the value of the car decreases. All right. Is this relationship linear or nonlinear? We don't know yet. We could graph it, which we will create a scatter plot later. But for now, because it's asking if it's linear or nonlinear, we're going to just do the first differences right away. So here we go. We have these two numbers, so on and so on. And I'm not going to write out the full subtraction, but I will do it kind of in my head, or if you want to do it on the side. But I have 17,000 minus 20,000, which is negative 3,000. So it loses 3,000. This value, the car loses $3,000 in value in the first year. In the second year, 14,000, 17,000, it's also 3,000. Oh, interesting. And then 11,000 minus 14, also 3,000 lost. And then 8 minus 11, also 3,000. So we could say, okay, this is linear. It's decreasing by the same amount every year. Um, I mean, is this realistic? Probably not, but we'll talk about that a little later. All right, so linear. Why is it linear? Because first differences are the same. Are constant, actually. I'll use the words. Constant means the same. We should use the math vocabulary. There we go. All right, moving on to scatter plot. So it says create a scatter plot. All right. I know that my age of the car is independent because the car is going to age no matter what. Value is going to depend on how old the car is. So I'm going to put age of the car. Car, and what's the other one? Value. So age of car. Okay, there we go. I should minimize this because I almost closed it. Value of car. There we go. Nice. Okay, now I'm scared. Did I save this? Okay, it's still recording. We're good. Nobody panic. There we go. All right, now we have to create a scale, but I do want to look at the questions that are following. It says estimate the age of the car if the value is 6,000 and estimate the value of the car at 6 years. Okay, so I'm going to try and fit 6 years here, which it shouldn't be too difficult. 1, 2, 3, 4, 5, 6, There we go. And maximum value was 20,000. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like I can go 2,000 at a time. And that should fit. If you are not sure about the scale, try it out. You can always erase it and fix it. Just use a pencil. That's kind of the most important thing. These guys look like sixes, but they are not. There we go. And 20,000. There we go. All right, first point, I'll use the red, was 0, 20,000. So it starts here, and then every year after that, it went down by 13,000. So first year was 17, second year was 14, oops. Then we have 11, then we have 8, and so on and so on. Oh no, it is wherever I put my hand, it's making this, but I shouldn't be doing that. Anyways, it's because I'm not in the, oh yeah, I am in tablet mode. Weird. Okay, so we have scatter plot. Now let's see what it says. Draw a line of, or line of best fit or a curve of best fit. Well, we determined that this is already linear, so it should be a line of best fit. So I will get that starting at 20,000, going through all of these points, something like this, maybe. There we go. Something like that. My graph is not the greatest, but it looks decent. It should be okay. All right. Um, so this is my line of best fit. It says estimate the value of the car when it's 6 years old. All right. 6-year-old car. We're using interpolating and extrapolating. In this case, it's going to be extrapolating because I'm going to my last point. I'm not going to my last point. I'm going after my last point. So I'm starting at 6. Oops. I have some glitches here. That's good. I'm starting at 6. Goes up to the line of best fit, something like that. And going over. There we go. So it looks like the value. So value. Oof, gotta adjust this quickly. Value of the car is $2,000 after 6 years. There we go. Then it says estimate the age of the car if its value is $6,000. Same thing, same process. There we go. Starting at 6,000 over and going kind of down here. All right. Because my graph is not the best thing, here we go. The answer for this one is 4.8 years, maybe. Age of the car is 4.8 years. Um, if the value is 6,000, now we should round off to years, and maybe if the graph is better, it should be, you know, a better answer, but around 4.8 years if the value of the car is 6,000. I think that's it for this question. Yes, so this was a good question because it went over everything. It summarized first differences. We talked about whether something's linear or non-linear. We talked about what a relationship is. We created a scatter plot, drew a line of best fit. We created a scale. We did some interpolating, extrapolating, everything here. So this is a really good summary of the whole chapter 5. So that's it for this lesson. Let's see, how long did that take? All right, 20 minutes, not too long. If you have any questions, please email me. And that is it. See you later. Bye.